Linearity does hold in this case because the equation appears to be true. As far as I can tell, we've got the right equation. So the linearity assumption does not say that you're drawing a line. It does not say that you're drawing a line. It says that the equation you write down has to be true. If you've had a class like linear algebra, let me just point out that this actually, although this equation doesn't look like it's linear because it's a parabola, it's linear in x and x squared in that it's constant times something plus constant times something plus constant times something. So it's linear in that sense, but we don't think of parabolas as linear, right? And I want you to see that a linear regression does not actually assume that you have a line. Rather, it assumes that the equation you write down to relate the predictor to the mean of the outcome is true. That's what linearity means. The second assumption is independence. So now we're getting into the assumptions that are going to sound a lot like what we have for t-tests. What kind of assumption, what kind of independence do I mean? Independence within and between subgroups based on X. And I'll explain what that means. Independence within and between subgroups based on X. So if I go back to the kind of picture I was drawing a moment ago, here's X, here's Y. I'll draw a check here to remember that that linearity was true there. 1, 2, 3, 4, 5, and I had a bunch of data points, right? That's what I just drew. Okay, so if we were talking about a t-test, we'd have only two groups, right? So you can imagine like only looking at this part of the picture. So think about what the independence assumption meant in the t-test context. We said we had independence between and within. When we said independence between, we meant that we had independence between the first group and the second group. In other words, knowing that a particular data point had been sampled to be included in the first group doesn't tell me anything about which data points are going to be sampled for the second group. So if you're thinking of the tuition example in colleges and comparing public to private, if Wellesley is selected by simple random sample to be included as a private school, that doesn't give me any information about whether UMass is going to be one of the colleges selected for the public schools. That's independence between groups. So we're generalizing that here. When we say we have independence between subgroups based on X, what we're saying is the fact that one particular data point was chosen for the data set that has X equals 1 doesn't tell us anything about whether any other particular data point that has X equals 5 is going to be selected. We're selecting the points independently between the different groups based on X. So here you can think of this picture I've drawn as an extension of a t-test, which just had 2 groups, to a case with 5 groups. And so independence between means independence between those 5 groups. Independence within thinks about just one group at a time. So if you're looking only at one subgroup based on X, you can think of reduce it to a t-test with only 2 groups. Think about a case where you're just drawing the private schools that are going to be in your data set, not even thinking about the public schools. Independence between says that the fact that I draw one particular unit to be in my sample for one group doesn't tell me anything about whether I'm going to draw some other unit. This is true if you have simple random sampling where the population is way bigger than the sample, or it's true if you do sampling with replacement. It's not actually technically true if you do simple random sampling for a data set where the population is small relative to the sample, because suppose I'm choosing students, suppose there's 5 people in my lab and that's my population, and I'm going to choose 2 of them to go to a breakout room. Once I choose one person, that changes the probability that you're going to be chosen, right? Because one of the spots got used up. So if the population is not much bigger than the sample, you do need to worry about independence within a group. But as long as the population is really big, this is usually not an issue. So this independence within and between groups that we had for pool t-tests or 2 sample t-tests extends to this case if you think about the regression data as just being subgroups defined by this X variable. Note here, let me pause and say that I previously, when connecting regression to trees, was talking about multiple predictors, but for now we're talking about one predictor, although everything I'm saying here extends. But it's simpler to just talk about one predictor here. Okay, so we said that linearity was a crucial assumption. Independence is also really important. So it's not, you can't say that regression is robust to either one of these assumptions. Independence is required for any sort of p-value or interval that you might try to create from your model. And we'll, of course, talk about how to come up with those. So here's a question for you. Let me draw a little picture. Suppose we have stock data. Here's X and here's Y, and maybe the X variable is day, and the Y variable is the value of a stock. And there's my data. My question for you is whether the independence assumption holds in this case.